Now, population growth. The size of a population for any species is not a static parameter. It keeps changing with time depending on various factors including food availability, predation, pressure, and adverse weather. In fact, it is these changes in population density that gives us some idea of what is happening to the population, whether it is flourishing or declining. Whatever might be the ultimate reasons, the density of a population in a given habitat during a given period fluctuates due to changes in four basic processes, two of which is natality and mortality. Immigration contribute to an increase in population density, and other two like mortality and immigration to a decrease. So natality refers to the number of births during a given period in the population that are added to the initial density. Mortality is the number of deaths in the population during a given period. Immigration is the number of individuals of the same species that have come into the habitat from elsewhere during the time period under consideration. And immigration is the number of individuals of the population who left the habitat and gone elsewhere during the time period under consideration. So if n is the population density at time t, then its density at time t plus 1 is n at time t plus 1 is equals to n जो पुराने टाइम पे था प्लस बर्थ प्लस इमाइग्रेशन, बर्थ रेट प्लस इमाइग्रेशन माइनस डेथ रेट minus immigration. You can see from the above equation that population density will increase if the number of births plus the number of immigrants, means b plus I, is more than the number of deaths plus the number of immigrants. Under normal conditions, birth and deaths are the most important factors influencing population density. The other two factors assuming importance only under special conditions. For instance, if a new habitat is just being colonized, immigration may contribute more significantly to population growth than birth rates. Now, growth models. Does the growth of a population with time show any specific and predictable pattern? We have been concerned about unbridled human population growth and problems created by it in our country, and it is therefore natural for us to be curious if different animals population in nature behave the same way or some show restraints on growth. Perhaps we can learn a lesson or two from nature on how to control population growth. Exponential growth. Resource, that is food and space. Resource availability is obviously essential for the unimpeded growth of the population. Ideally, when resources in the habitat are unlimited, each species has the ability to realize fully its innate potential to grow in number, as Darwin observed while developing his theory of natural selection. Then the population grows in an exponential or geometric fashion. If in a population or size n, the birth rates, not total number but per capita births, are represented as b, and death rates again per capita death rates as small d, then the increase or decrease in n during a unit time period t, that is dn by dt, will be dn by dt is equals to birth minus death into n. So let b minus t be r. So dn by dt is equals to rn. So the r in the equation is called the intrinsic rate of natural increase and is a very important parameter chosen for assessing the impacts of any biotic or abiotic factor on population growth. To give some idea about the magnitude of R values For the Norway rat, it is 0.015, and for the flower beetle, it is 0.12. In 1981, the R value for human population in India was 0.0205. Find out what the current R value is. For calculating it, you need to know the birth rates and death rates. The above equation describes the exponential or geometric growth pattern of a population and results in a J-shaped curve when we plot n in relation to time. If you are familiar with basic calculus, you can derive the integral form of the exponential growth equation as nt is equals to n naught e to the power rt. So this one is the exponential growth. So nt is the population density after time t. N naught is the population density at time 0. R is the intrinsic rate of natural increase. E is the base of natural algorithm. The value of E is 2.71828. Any species growing exponentially under unlimited resource conditions can reach enormous population densities in a short time. Darwin showed how even a slow growing animal like elephant could reach enormous numbers in the absence of checks. The following is an anecdote popularly narrated to demonstrate dramatically how fast a huge population could build up when growing exponentially. So this one is the normal, just an example of exponential growth in which the Prime Minister plays a chess game. Okay. Now logistic growth. No population of any species in nature has its disposal unlimited resources to permit exponential growth. This leads to competition between individuals for limited resources. Eventually, the fittest individual will survive and reproduce. The governments of many countries have also realized this fact and introduced various restraints with a view to limit human population growth. In nature, a given habitat has enough resources to support a maximum possible number, beyond which no further growth is possible. Let's call this limit as nature's carrying capacity for that species in that habitat. A population growing in a habitat with limited resources show initially a lag phase, followed by phases of acceleration and deceleration, and finally an asymptote when the population density reaches the carrying capacity. A plot of n in relation to time t results in a sigmoid curve. So this one is the logistic growth curve, sigmoid curve. This type of population growth is called Verhulst-Pearl logistic growth and is described by the following equation. dn by dt is equals to Rn k minus n by k. So where n is the population density at time t, R is the intrinsic rate of natural increase, k is the carrying capacity. Since resources for growth for most animal populations are finite and become limiting sooner or later, the logistic growth model is considered a more realistic one. Gather from government census data the population figures for India for the last 100 years, plot them and check which growth pattern is evident.